Welcome back to Sleep with Science, where we gently explore the universe, one peaceful idea at a time. If you're lying in bed, wrapped in blankets, or floating between thoughts, you're exactly where you need to be. Tonight, we're building a universe quietly, patiently, and entirely from nothing. Now, fair warning, this video might be a bit too fascinating. If it keeps you up late, I'm sorry. But if you're going to be wide awake at 1 a.m., you might as well learn how. Galaxies are born from invisible particles and simple rules. There are worse ways to lose sleep. If you enjoy calm, thoughtful videos filled with wonder, please give this one a gentle like and tap subscribe. It helps more curious minds find their way here. And if you're feeling social, share where you're listening from and what time it is. There's something beautiful about people all around the world drifting off under the same stars. Now, take a deep breath. Let your shoulders relax. Let your thoughts slow to the pace of starlight, and let's begin. Imagine you're handed a blank canvas, not of paint or pixels, but of endless potential. And instead of brushes, you paint with equations, not trees or skies, but galaxies, dark matter, stars, and time itself. This is what scientific simulations are all about. Simulation tries to recreate the universe inside a computer. Not like a sci-fi matrix, but a real experiment using the known laws of physics to model what's happening billions of light years away. These simulations aren't just pretty visuals. They're deeply mathematical worlds. Scientists use them to test ideas, change variables, rerun events, and see how galaxies grow or stars form. It's like a sandbox for reality. But let's be clear, simulations aren't photos. They're more like memory sketches drawn from the equations of physics. Every galaxy, star, and dark matter halo is created from rules. Rules about how gravity works, how gases move, how matter spreads through time and space. These rules are too complex for a blackboard, so scientists use supercomputers. Some run for days or weeks. In movies or games, simulations focus on visuals. A crashing wave might look real, but doesn't follow real physics. Scientific simulations, though, aren't judged by beauty. They're judged by accuracy. If a galaxy spins too fast or forms too many stars, it's wrong, no matter how stunning it looks. That's the fascinating part. Scientific simulations live between art and science. They need creativity, choosing what forces to include, how to model gas, how to simulate time. But they're also bound by hard data from telescopes, satellites, and detectors. It's like writing a song using only a few allowed notes to build even a simple simulation. Scientists begin with a kind of digital Big Bang, a cloud of particles spread across virtual space. Each particle can represent a galaxy's worth of matter. From there, gravity and expansion take over. Time moves forward in tiny steps, each one calculating how everything pulls and pushes everything else. Eventually, patterns emerge. Matter, clumps, filaments stretch, voids appear. It starts to look like the cosmic web we see in real space. But how do we know it's accurate? We compare. Real data from galaxy surveys, background radiation, and gravitational lensing are matched with what the simulation creates. If they align, great. If not, we tweak the settings and try again. Still, no simulation is perfect. It's only as good as the physics behind it. If we're missing something, like the nature of dark matter or how magnetic fields behave, that hole shows up. It's like baking a cake and forgetting sugar. It might rise, but it won't taste right. Sometimes we don't even know what we're missing, and that's the point. A failed simulation isn't a mistake, it's a clue. Maybe dark matter isn't what we think. Maybe stars form differently. Simulations let us run experiments we can't do in real life. We can't rewind the universe, but we can do it in code. What if gravity was stronger? What if there were fewer black holes? What if the early universe was smoother? Each simulation becomes a what-if machine, a way to explore the past and understand the present. These computer universes often feel strangely alive. Galaxies grow arms, collide, birth stars, all from code. Watching them is like watching real physics unfold. Some simulations zoom in a single supernova, a gas cloud, a black hole. Others study how planets form or how chemistry unfolds in star nurseries. And it's not just space. We use simulations for earthquakes, weather, disease, climate, even quantum physics. The idea is the same. Build a world from math and see what it does. So when we talk about simulations, we're not describing illusions. We're talking about mathematical mirrors, careful reflections of what we think the universe is doing. Not made of glass, but of gravity, geometry, and time. In a way, it's like dreaming, not in images, but in equations. And in those dreams, galaxies begin to spin. Before we can build galaxies, we need to define what a galaxy even is. Before modeling gravity, we have to understand how mass behaves. And before a single particle moves, we need a rule book. That rule book is physics, and its language is mathematics. At its core, a simulation begins with particles, but not particles like atoms or electrons. In cosmology, a particle is more like a chunk, a simplified piece of the universe. One of these might represent a whole dwarf galaxy or a massive cloud of gas 1,000,000 light-years across. It's not about tracking every atom. It's about capturing the big picture, how that mass behaves on cosmic scales. These particles don't look like anything. They're just numbers in a virtual 3D grid. Each one has a position, a velocity, maybe a temperature, sometimes even a chemical makeup. As the simulation runs, those values evolve based on physics. The goal: to watch how structure forms, where things go, how they clump, what appears. And when but particles alone don't do anything without forces acting on them. And in the vast theater of space, the leading actor is gravity. Gravity sculpts the universe. It pulls matter together, forms galaxies, merges clusters, and builds the invisible skeleton made of dark matter. In simulations, gravity is usually modeled using Newton's laws. Sometimes general relativity is used, but only in small, specialized models. It's just too heavy for even powerful computers to handle at large scales. Simulating gravity might sound simple. Calculate how one object pulls on another. But with billions of particles, the math becomes massive. Every particle affects every other one. To make it manageable, simulations use shortcuts. One clever trick is the tree algorithm. Instead of calculating each force separately, it groups distant particles together. It's like treating a distant galaxy cluster as a single blob. This saves time while still being accurate. Next comes electromagnetism. Gravity rules the large-scale cosmos, but electromagnetism matters when we look closer, especially with gas. Hot gas glows, cools, collapses. Magnetic fields shape the flow of charged particles, influence star formation, and stir turbulence. In clouds of gas, large simulations simplify this. But in zoomed-in models of star-forming regions, electromagnetic forces become essential. And then there's hydrodynamics, the physics of fluids in space. Gas acts like a fluid, especially when it's hot and tumbling through gravity wells. Simulations use techniques to model how fluids move, how shock waves spread, pressure builds, and turbulence grows. One popular method is smoothed particle hydrodynamics. It treats gas as a fluid made of overlapping particles, each influencing its neighbors. It allows scientists to simulate messy, flowing behavior without needing rigid structure. Now, let's talk about the invisible backbone of the cosmos. Dark matter. It can't be seen. It doesn't glow or interact with light. But it outweighs all visible matter many times over. In simulations, dark matter is given its own type of particle. It doesn't feel electromagnetism so it passes through itself without resistance, but under gravity it clumps together. These clumps become the massive halos that anchor galaxies and clusters. Dark energy, on the other hand, is subtler. It's not a particle, but a property of space itself. It controls how the universe expands. In simulations, dark energy shows up in the background, shaping how fast space stretches over time and how quickly structures can grow. All of these particles, forces, and cosmic energies must be organized into something a computer can understand. That's where the equations come in. These aren't simple numbers. They're long, complex systems of partial differential equations, messy, non-linear, and deeply connected. They describe how things move, heat up, cool down, clump together, or drift apart to simulate time. Computers break it into small steps, like a ticking cosmic clock. At each step, it calculates how the universe should look. But getting this right is tricky. Too large a step, and the results become inaccurate. Too small, and the simulation takes forever. Scientists spend hours just tuning this balance, trying to move fast without losing precision. And beneath it all are the constants of nature, the speed of light, the gravitational constant, Planck's constant. These numbers define everything from how mass bends space to how fast energy can move. They are the dials on the cosmic control board. Even the tiniest tweak would create a universe unlike our own. And yet, even with all this effort, simulations still rely on approximations. Some processes are just too detailed to simulate directly, like the exact explosion of a supernova or the fine-grained dance of stars in a crowded galaxy core. To handle this, simulations use subgrid models, simplified rules that stand in for missing complexity. For example, rather than simulate every supernova, the model might just inject a burst of energy when a gas cloud reaches a certain density. It's like drawing a sketch instead of painting every stroke. These simplified rules must be carefully tuned. A small change can lead to huge differences. Simulating gravity is one thing. Simulating the swirling chaos inside a galaxy is something else entirely. Still, underneath all the layers, simulations are built from just a few key ideas. Particles that represent mass forces that shape the equations that guide their motion and time. Until it works, suddenly, out of cold math and silent code, a universe begins to grow. Galaxies spiral, clusters collide, voids stretch open. The simulation becomes strangely lifelike, not made from stardust, but from ideas. It's not divine, it's understanding. A simulation doesn't just mimic reality, it shows that we can describe it. And even though it's not perfect, it reveals how far curiosity and math can take us not so long ago. The idea of simulating a universe was science fiction. Computers were huge, slow, and weak. But curiosity moves faster than machines. In the mid-20th century, a few daring scientists asked a wild question. What if we could model the cosmos on a computer? They didn't imagine 3D galaxies or visual effects like we have today. They just wanted numbers on a grid, the basic rules of gravity and expansion. Run forward in digital space. It was like trying to build a castle using just a teaspoon and a spreadsheet, but the dream had begun. Early computer simulations could only handle a few particles, maybe a dozen at most, sometimes even less than 10. That might sound silly today, but back then it was a major breakthrough. For the first time, scientists could actually watch gravity work, not just on a chalkboard, but in motion, right on a screen. It was basic, yes, but it changed everything. By the 1970s, computers had improved just enough to try bigger experiments. Scientists like Spa-Ease and his team began using what they called unbody simulations. That just means simulations where n is the number of objects' particles that pull on each other using gravity. These early versions still only used a few hundred particles, but that was enough to notice something surprising. Matter doesn't stay spread out. Over time, gravity pulls it into clumps, threads, and empty spaces. Without any complex rules, a large-scale shape of the universe started to form. All from gravity. These simulations didn't include gas, stars, or dark energy. They only followed Newton's laws of gravity. But they hinted at something deeper. Maybe the universe, with all its chaos, follows simple rules from the very beginning. Maybe it organizes itself naturally. Then came the grids, to simulate larger areas of space. Scientists needed a better way to organize data. One method was to split space into invisible 3D cubes and track how matter and energy moved through them over time. These grid models weren't as flexible as particle-based ones, but they had an upside. They handled flowing gas much better. Since gas expands, compresses, and radiates energy, it needed a space to move through, and grids provided that space. By the 1980s, these simulations had grown in size and complexity. Scientists started mixing both grid-based gas models with unbodied gravity systems. These hybrid simulations could show both dark matter and gas, though still in basic form. Yet, the results were eye-opening. For the first time, a simulated universe showed something familiar: the cosmic web. Huge clusters, connected by long filaments with big, empty voids in between. It looked like galaxies, were forming as part of a much larger structure. The universe wasn't just growing, it was shaping itself. But to truly simulate how the universe formed, one thing was missing: dark matter. Dark matter was still a new idea back then. Astronomers had noticed that galaxies were spinning too fast. There had to be extra gravity holding them together. The answer? Dark matter. It's invisible, doesn't give off light, but it still has mass and pulls on everything around it. When researchers added dark matter to their simulations, the whole picture changed. Dark matter doesn't form stars or give off light. It just drifts through space, guided only by gravity. In simulations, it formed huge spherical halo zones where it was densest. And right in the center of these halos, galaxies, like tiny pearls inside invisible shells. This discovery changed everything. It gave the simulations a backbone, something to build galaxies around in the 1990s. Computers became powerful enough to handle millions, then billions of particles. These particles represented both gas and dark matter. The results were amazing. Massive threads of dark matter connected galaxy clusters like invisible roads. Shock waves flowed through gas clouds. Suddenly, simulations began to look just like what astronomers were seeing in the sky. They weren't just guesses anymore. They were accurate models. One big shift during this time was the move from ideal simulations with clean, made-up starting conditions to more realistic ones based on real data. Scientists used light from the cosmic microwave background, the leftover glow from the Big Bang to set the original conditions in their models. These small changes in temperature and density acted like seeds from which the universe could grow. It was like giving the simulation a baby photo of the universe and asking it to grow it into what we see today. The phrase "universe in a box" became popular. A simulation would take a chunk of space, maybe 100 million light years widened, fill it with virtual matter. Then it would evolve that box step by step over billions of years, using the laws of physics. Every particle's movement was tracked. The goal wasn't to simulate the whole universe, but enough of it to capture the patterns we actually observe. These box simulations revealed a lot. They showed how dark matter halos combine, how galaxies fall into clusters, and how giant voids form. They confirmed that gravity plays the main role in shaping everything. And they helped support the cold dark matter model, the leading theory of how structure forms in the universe. But maybe most importantly, simulations gave scientists a way to test ideas. You can't rewind the real universe. You can't just change something and see what happens. But in a simulation, you can. You can adjust the amount of dark matter, change how fast the universe expands. Or try out a new theory and then press run to see what the digital universe does. The early years of these simulations were limited. The resolution was low, and the rules were simple, but the groundwork was in place. Scientists had learned that gravity could turn simplicity into complexity, and that computers could show us patterns too big, too slow, or too far away to study otherwise. What began with a few dots on a screen had grown into something incredible, a whole new way to understand not just what the universe is, but what it could have been nor still might become. And all of it, somehow, inside a box. By the early 2000s, a group of scientists set out to create something huge, a digital universe so big, so detailed, and so realistic it would push computers to their limits. This wasn't sci-fi or an academic. Side project was real, and it would go on to become one of the most important simulations in the history of cosmology. They called it the Millennium Simulation. Its goal was to model the entire visible universe, not perfectly, of course, but with incredible detail for its time. It ran in 2005, created by the Max Planck Institute for Astrophysics in Germany. It simulated how the universe grew from 400,000 years after the Big Bang, all the way to today, over 13 billion years of cosmic change, all packed into a stunning digital experiment. To do it, they used 10 billion particles, not real ones, but virtual ones, each one standing in for a huge chunk of dark matter. All together, they filled a cube of space 2 billion light-years wide. Pause for a second. 2 billion light-years. That's about 1/15 of the entire observable universe. Imagine simulating a box of space so big that it contains tens of millions of galaxies. Then imagine tracking each of those galaxies over billions of years to see how they move and evolve. It was like trying to simulate the weather not for one city or for 1 week, but for a whole planet over billions of years. And yet, the Millennium Simulation did exactly that. But what made it special wasn't just how big it was the accuracy, the ambition, and the deeper meaning behind it. For the first time, scientists could watch the universe evolve, not in theory or through a telescope, but as something alive. They could watch dark matter halos form, combine, and grow. They could study how galaxies came to be inside these invisible halos of dark matter. Galaxies formed, and not in isolation. They grouped into long strands, vast bridges, and wall-like structures across the universe. And scientists managed to recreate all of this inside a computer. To run such a large-scale simulation, massive computing power was needed. The Millennium Simulation was powered by a supercomputer called the Garching Reconcentrum, an advanced machine for its time. For months, it solved the equations of gravity, updating the position and velocity of every particle in the universe step by step, simulating the flow of cosmic time. At first, the simulation didn't look like much. It produced raw data, petabytes of it, filled with trillions of numbers that described where each particle was at each moment in time. But once that data was visualized, something incredible appeared. A digital universe that looked eerily familiar. Filaments, clusters, and vast empty voids, all taking shape like a reflection of the real cosmos. It was as if the structure of the universe had been recreated from scratch. The Millennium simulation focused on just one key ingredient of the universe: dark matter. That's the invisible scaffolding that shapes cosmic structure. Regular matter, like gas, stars, and galaxies, wasn't directly simulated. Instead, scientists use semi-analytic models. These are mathematical tools that overlay visible structures onto the dark matter map based on how we think galaxies might form and evolve. It's like baking a cake with a basic structure first, and then decorating it based on what we observe in the real universe, using data from telescopes like Hubble and surveys like Sloan. The result: a simulated universe that didn't just match what we saw, it helped explain it. This was a turning point. With the Millennium simulation, scientists could do virtual astronomy. They could point a virtual telescope in any direction and study what appeared, then compare those mock observations with real data to find any differences. Did the simulation predict fewer galaxies in one region than we actually observed? That could mean either the model missed something, or our instruments were picking up something unexpected. The simulation also helped resolve major debates. One of the biggest was about the nature of dark matter. Some scientists believed it might be warm, fast-moving particles that smooth out small structures. Others believed it was cold, slow-moving particles that allow galaxies and clusters to form more easily. The Millennium simulation strongly supported the cold dark matter theory, showing that it produced the cosmic web we actually see in space. The name Millennium wasn't just dramatic, it reflected the scale of the simulation. It covered billions of years of cosmic evolution, and it set a new benchmark for astrophysics. Other teams soon created their own simulations with more detail, more physics, and more computing power. But for years, Millennium remained the gold standard. It also raised profound questions. If we can simulate the universe with this much accuracy, what does that say about our understanding? Does it mean we've figured it all out? Not exactly. The simulation worked by making educated assumptions about dark matter and the universe's starting conditions. Those assumptions were based on the best data at the time, but they're still approximations. In the end, the Millennium simulation was an incredibly smart, detailed guess, one that happened to align closely with reality. Still, it had limits. While it captured the large-scale structure of the universe, its resolution was coarse. Each particle represented an enormous mass, millions of times heavier than our sun. So it couldn't show small-scale features like individual galaxies or satellites. Other simulations were needed for that dot, but Millennium showed that simulating the universe wasn't just possible, it was powerful and beautiful. The visualizations created from the data were stunning webs of light tracing the dark structure of space, like frost on a cosmic window. These images didn't just inform scientists, they inspired them. Many felt that, somehow, they were looking at the bones of reality. Some joked the simulation was so detailed. Maybe we're living inside one. It was just a joke. Or was it? If a simulation can look and behave exactly like the real universe, how do we define what's real? That's a philosophical question, and the simulation can't answer it. But it does make the question harder to ignore. The Millennium simulation was a breakthrough. The moment simulations became real tools for testing theories, challenging assumptions, and studying the cosmos like a living experiment. It reminded us that even with invisible forces and unknown particles, we can still build something astonishingly close to truth. And it all started with one bold idea: 10 billion particles inside a cube large enough to hold a slice of eternity. Then came something even more ambitious. In 2014, a global team of astrophysicists launched the illustrious simulation, the next big step in simulating the universe. While Millennium focused mainly on dark matter, Illustrious went further. It tracked not just the invisible structure, but also how gas flowed, stars ignited, black holes fed, and galaxies evolved. And it did all this with visuals so stunning, even veteran scientists were amazed. Earlier simulations relied on simple rules to approximate visible matter. But Illustrious aimed to model everything: how galaxies grow, merge, interact, and scatter light across cosmic time. The result wasn't just more accurate, it was almost lifelike. Spiral galaxies spun gracefully. Giant elliptical galaxies glowed with heat from ancient collisions. Gas moved like waves through space, stretching and flowing like a cosmic tide. The numbers behind it were just as impressive. Illustrious simulated a cube of space about 350 million light-years wide, using over 12 billion resolution elements. These included particles for dark matter, gas, stars, and black holes. Each element had properties like mass, speed, temperature, and chemical makeup, all evolving over time based on the laws of physics. At the heart of this simulation was a powerful algorithm called unravel. Most simulations use a fixed grid to divide space. Unravel used a moving mesh, a flexible grid that flowed with matter. This allowed high accuracy without wasting computing power, especially in complex areas like star-forming regions or swirling gas clouds. It was like watching a digital universe breathe and expand. But it wasn't just the detail, it was the scale. The team ran several simulations at different resolutions to balance depth and scope. They also included realistic feedback from stars and black holes. When a star explodes, it sends out energy that slows future star formation. Supermassive black holes do the same on a much larger scale, blasting jets of hot gas that can push material out of entire galaxies. These feedback effects are tough to model. They happen on small scales, but shape the whole universe. Illustrious managed to simulate them in a way that felt both scientific and cinematic to capture this complex behavior. Scientists used subgrid models in the simulation, generate galaxies that looked surprisingly real. When they compared the simulated galaxies to real ones taken from telescope surveys and deep field images, they noticed something amazing. The shapes, sizes, and even colors of the galaxies matched up closely. Still, the simulation wasn't perfect. Some galaxies turned out too large or too tightly packed. In certain areas, it formed too many stars, a common issue with early models. But the goal wasn't perfection, it was progress. The illustrious project showed what happens when physics, computer science, and a little creativity come together. And about that creativity, the visuals from Illustrious were stunning. The team used the raw data to make animations and images that looked like cosmic paintings, glowing gas clouds, galaxies spinning like fireworks. The results were breathtaking. These visuals weren't just for decoration. They helped scientists see how matter moved, how energy spread, and how different cosmic forces shaped galaxies. But something unexpected happened, too. People outside of science artists, teachers, even poets were captivated. These simulations became more than just research tools. They became a window into a hidden universe, full of motion, color, and mystery, building on Illustrious. The team launched a new project, Illustrious TNG. TNG stands for the next generation. This new suite of simulations improved almost everything. The biggest one, called TNG 300, was nearly 10 times larger than the original. It had better models for magnetic fields, star winds, feedback from galaxies, and even the way elements like carbon and oxygen spread across space. For the first time, Scientists could track how galaxies got their heavy elements, the same ingredients that make planets and life possible. Illustrious TNG also recreated all kinds of galaxies, spirals, irregulars, massive elliptical systems, all looking like the real thing. It even showed how galaxies evolved depending on where they lived, alone in empty space, clustered with others, or streaming along the filaments of the cosmic web. The simulation revealed how galaxies interacted with their environments, whopping gas, forming bursts of stars, or going completely silent after shining brightly in their youth. One surprising insight was about supermassive black holes. These weren't just monsters at the center of galaxies. They actively shaped how galaxies grew. When black holes pulled in matter, they released huge amounts of energy. This could heat up gas, stop new stars from forming, or even blast material into deep space. In TNG, this feedback was crucial for simulating the quiet, massive galaxies we see in the real universe today. And like the first illustrious project, TNG produced mesmerizing visuals. Dark matter stretched out like glowing spiderwebs. Galaxies twinkled like fireflies in space. Color maps showed how gas temperatures shifted and flowed. It wasn't just art, it was storytelling, told through code and physics. But beneath the beauty was solid science. These weren't random guesses. They were testable ideas based on theory and observation. Researchers could tweak the models and rerun them. What if stars formed faster? What if black holes were more powerful? What if dark matter behaved differently? Each test was part of a conversation between what we know and what we imagine could be true. These simulations also remind us how far science has come. Early models tracked just a few particles. Now, they handle tens of billions of elements tracing galaxies across billions of years. But even now, they aren't perfect. Assumptions still exist. Some mysteries remain unsolved. Yet the story tell is powerful. A universe that follows rules but is still full of surprises, where simple physics builds complex beauty, where galaxies form, evolve, and fade in a quiet cosmic rhythm. Illustrious and TNG are more than simulations. They are ways to understand our place in the universe. They invite us to be part of the story, observers, yes, but also participants. And if that story just happens to look gorgeous while it plays out, all the better. At first glance, a galaxy simulation looks dull. Just numbers, coordinates, masses, temperatures, a jumble of data flying through digital space. But hidden in those numbers is something beautiful. With the right tools and enough time, those numbers become galaxies spinning, glowing almost alive. It all begins with motion. Every particle, whether it represents dark matter, gas, or a star, has a place and a speed. These particles move. According to physics, in each step of time, maybe 1,000,000 years, the simulation calculates how each one reacts to gravity, pressure, and energy. Gravity is the first artist. Even before stars exist, it starts pulling matter together. Small clumps grow into larger ones. This process, called gravitational instability, forms halos of dark matter. These halos are like invisible skeletons that galaxies will grow around. Dark matter doesn't shine, but it holds everything in place. Without it, galaxies would drift apart like mist. As the dark matter halo grows, it pulls in gas, hydrogen, and helium left over from the Big Bang. This gas falls in, heats up, and starts to swirl. Now the real action begins in the simulation. Gas is modeled using fluid dynamics, tracking how it flows, compresses, and cools. Tools like smooth particle hydrodynamics or grid-based solvers follow every twist and turn. The gas isn't just drifting, it's alive with movement. Some areas get cold and dense enough to form stars. But how does the simulation know when a star is born? That's where clever programming comes in. Real star formation is messy. It involves magnetic fields, clouds of molecules, and chaos. The simulation can't model every detail. Instead, it uses a recipe star formation algorithm. When a gas region meets certain conditions, high density, low temperature, and enough mass, it's marked for star formation. The simulation turns part of that gas into a star particle. A star particle doesn't represent one star. It's usually a stand-in for millions. Each particle has properties like age, mass, and how many heavy elements it contains. Over time, these star particles evolve. Some fade. Some explode as supernova, sending energy and matter back into space. This feedback affects the surrounding gas and the next generation of stars. And this is where the beauty shines through. The raw data is still numbers. But when we turn it into visuals, brightness for mass, color for temperature, contrast for density, we begin to see galaxies take shape. Spirals unfold. Ellipticals glow like cosmic clouds. Gas flows between galaxies like quiet fireworks. And the simulation didn't draw any of it. It just followed. Physics and beauty appeared. These visuals aren't just for show. Just use them to study how stars form, how gas behaves, and how feedback changes everything. By comparing these simulated galaxies to real images from telescopes like Hubble or JWST, with the help of the James Webb Telescope, scientists can now test how well their universe simulations match reality. Do the fake galaxies have the right colors? Do they spin at the right speed? Are there both old and young stars inside them? If the answers are yes, it means the simulation is working. If not, the scientists go back to their code and adjust things. What's amazing is how natural these images feel. You don't need to be an expert to recognize a spiral galaxy or two. Notice when something looks wrong. Our brains are great at spotting natural patterns. Galaxies, even though they're massive and complex, often follow shapes we've seen before. Watching them form in a simulation is like seeing a flower bloom in slow motion, but also makes perfect sense. Sometimes the most incredible features aren't planned at all. Simulations can create star streams from destroyed galaxies, swirling gas like ribbons, or huge empty voids that look almost too perfect. These things weren't designed, they just happen on their own through math, physics, and time. That's what makes simulations powerful. They don't just show us what we already know. They show what might be out there. Even mistakes are useful. If a simulation doesn't match the real universe, it means we've got something wrong. Maybe the model needs to change, or maybe there's new physics we haven't discovered yet to turn numbers into images. Scientists use special visualization tools like YT, OpenSpace, and custom software. These tools add color, simulate lighting, and let scientists zoom through cosmic structures. Some even create movie-like fly-throughs of entire virtual universes. You can drift past fake galaxies like a slow-moving comet. The results are a mix of science and art, a way to make the invisible visible. Simulations also let us speed up time. We can watch a galaxy take shape in seconds, spinning, lighting up, and colliding with its neighbors. In real life, this would take billions of years, but in a simulation, it's just a few frames. These digital galaxies aren't just copies of what we've seen. Sometimes they show us what we haven't yet discovered. Maybe it's a strange galaxy merger, or a gas cloud we'll only spot with future telescopes. Simulations help us imagine the unseen parts of the universe. They remind us that nature follows rules. If we understand those rules just a little, we can build pieces of the cosmos ourselves. Not with atoms, but with algorithms. Not with telescopes, but with code. And from that digital world, galaxies are born. They glow, they spin, they evolve. It almost feels real. Not because we faked it perfectly, but because we understood just enough to let the universe unfold on its own. These aren't just pixels pretending to be galaxies. In a way, they are galaxies built from gravity, physics, and the language of math. They speak in patterns, one data point at a time. Now, imagine painting a landscape, but the most important part is completely invisible. The trees sway, rivers twist, mountains cast shadows. But something huge and silent holds it all together. That's what it's like simulating dark matter. You can't see it or touch it. No telescope can take its picture. Yet in cosmology, dark matter is the invisible framework. It shapes galaxies, connects cosmic filaments, and stops the universe from flying apart. So, how do you simulate something so mysterious? First, we admit we don't know exactly what dark matter is. It's not made of atoms. It doesn't emit, reflect, or absorb light. It doesn't form stars or planets. But it does affect gravity. And that's where the simulation begins. Back in the 20th century, astronomers noticed something strange. Galaxies were spinning too fast. Visible matter alone wasn't enough to hold them together. It was like a carousel spinning wildly, but with no riders visible yet. The horses stayed in place. The only explanation was hidden mass, dark matter. In simulations, gravity is the great equalizer. If something has mass, it affects everything else. So scientists can include dark matter by giving it mass and letting gravity do the work. Even if we don't know exactly what dark matter is, we can guess its behavior based on how the universe looks today. To begin, scientists use data from the early universe, especially the cosmic microwave background, as a starting point. This shows tiny differences in the density of matter shortly after the Big Bang. Then they spread dark matter particles across the simulation using that map. These particles aren't tiny specks. They represent huge clumps of invisible mass, sometimes as much as several million suns. Dark matter doesn't behave like gas. It doesn't glow or cool. It simply floats, slowly collapsing under its own gravity. Over billions of years, these particles form halos-dense regions that grow by merging and pulling in more matter. Inside these halos, galaxies can form. Outside them, space stays mostly empty. Dark matter becomes the scaffolding for the universe, the hidden skeleton. Simulations show that it arranges itself into a massive cosmic web. Long filaments stretch across space, connecting at nodes where halos cluster together. These are the birthplaces of galaxy groups. Between them, giant voids remain. This structure appears both in simulations and in real telescope data. That's how we know our models are close to the truth. Even more surprising, simulations that only use dark matter, no stars, no gas con, still recreate the universe's large-scale structure. That's how important it is. But dark matter isn't the whole picture. To simulate galaxy formation, you need ordinary matter to gas that can cool, light up, and form stars. Unlike dark matter, gas behaves in complex ways. It compresses, heats, collapses, and explodes. Early on, gas and dark matter moved together, but over time, their paths split. Gas started forming stars and galaxies, while dark matter quietly shaped space in the background, like a conductor setting the tempo without playing a single note. Big challenge in simulating dark matter is choosing how much detail to include. Since we can't observe it directly, we rely on theories. The most popular is cold, dark matter particles that move slowly and form small structures. But others suggest warm, dark matter, which moves slightly faster and smooths out smaller features. The differences show up in the results. Cold, dark matter makes a detailed universe full of small galaxies and thin threads. Warm, dark matter makes a smoother universe with fewer small things. By comparing these simulations to telescope surveys, scientists can test which model fits better. For example, if the simulation predicts hundreds of dwarf galaxies around the Milky Way, but we only see a few dozens, that tells us something might be missing when it comes to dark matter. Scientists still don't fully agree. Some believe we've got the basics right, while others think we might only be close, not quite there yet. Simulations reveal something fascinating. The way dark matter forms halos. These halos have dense centers and softer outer layers. They are not hard spheres, more like soft, fuzzy clouds shaped by billions of mergers over time. The bigger the halo, the more likely it is to host a massive galaxy or even clusters of galaxies. And nearly all large halos hide something even stranger at their center, a supermassive black hole thriving in the darkness. The real beauty appears when we combine dark matter models with galaxy formation simulations. Together, they don't just match what we see in the universe, they help explain it. They show where galaxies form, how clusters grow, and why the universe appears the way it does, from vast scales to smaller structures. Still, we haven't found a single dark matter particle in the lab. We don't know what dark matter really is, a WIMP, an axion, or something we haven't discovered. Yet in simulations, it acts with surprising consistency. It holds galaxies together and shapes the universe through gravity silently. Envy's IB. It's like listening to an instrument you can't hear but still feel in the music. Without it, the rhythm falls apart. When it's included, everything fits together. That may be the strangest part. The thing we understand least might be the one holding everything in place. Simulations teach us that believing in the unseen isn't blind faith, it's seeing the same patterns over and over. It's learning to recognize a quiet but powerful presence. Even if we can't see dark matter, we witness its fingerprints in every spiral galaxy, every bending of light, every cosmic cluster drifting across space. And in simulations, dark matter comes alive, not in light, but in gravity, guiding everything from the shadows. But every simulation starts with choices. What to include and what to skip. No matter how strong the computer is or how smart the code, it can't model everything at once. And that's not a problem. It's how science works. Simulations are not mirrors of reality. They're maps, simplified tools to help us understand complex truths. Cosmological simulations aim to capture the big picture, how galaxies form, how matter moves, how the universe evolves. To do this, they rely on shortcuts and assumptions. Take resolution. Just like a photo has pixels, simulations have resolution points, particles, cells, or grid spots. More points mean more detail, but we can't simulate every atom or every star. Instead, simulations group things. A single star in the code might actually represent a whole cluster. A gas cell could stretch across light years. This smooths out chaotic physics and replaces it with averages, educated guesses, tiny scale events. Like a single star explosion or the swirl of gas clouds are not simulated directly. Instead, their effects are added using simplified rules called subgrid models. These are practical recipes that help the simulation mimic reality, even if the real process is much more complex. Take star formation. In real space, it depends on chemistry, magnetic forces, dust, and more. In simulations, it might be triggered when gas reaches a certain density and temperature. Scientists adjust these thresholds to make the simulated galaxies look like the real ones. But if the settings are off, the simulation either makes too many stars or none at all. Then there's feedback. How stars and black holes push energy back into space. In real life, exploding stars send out wild shock waves, and black holes can blast matter across galaxies. In simulations, this is done in simpler ways, like injecting energy into gas cells. But space isn't neat. Sometimes the simulation doesn't inject enough, or it goes too far and stops stars from forming. Magnetic fields are another tricky element. These invisible forces shape gas and guide particles. This using advanced physics, but many skip it to save processing power. Cosmic rays, high-energy particles, are often left out too, even though they could influence star formation and gas flows. New research suggests they may matter more than we thought. Even gravity isn't always simulated in full detail. Most simulations use Newton's gravity, which works well in most situations. But according to Einstein, gravity is actually the bending of space and time. In places like the early universe or near black holes, this difference could matter. But adding Einstein's equations is complex. So most models stick with Newton's simpler version. Chemistry is also simplified. Real gas clouds are made of many elements, not just hydrogen and helium. These metals affect cooling, star formation, and even how light travels. Tracking all these elements would be ideal, but it's too expensive computationally. So most simulations use a single value to represent all metals, losing the fine detail. Radiation is another simplification. Light heats gas, ionizes atoms, and pushes dust. But modeling how it interacts with everything is difficult. Some simulations use basic methods, while others assume even lighting or simple light sources. That works at large scales, but misses small, important effects, like how a star cluster can carve out a bubble in a gas cloud. One of the biggest unknowns is still dark matter. Simulations model its gravity perfectly, but not the particles themselves, because we don't know what they are. We assume dark matter is cold, doesn't collide, and doesn't interact because that fits observations. But if dark matter behaves differently, our models might be slightly off. Dark energy is another mystery. Most simulations treat it as a constant force causing expansion. But what if it changes over time? What if it interacts with other things? Those models are harder to simulate. So many just stick to the simple version. All these limits add up. And while simulations do a great job matching much of the universe, they're not perfect. Sometimes, when a simulation doesn't match real observations, it's not the universe that's wrong, it's what we left out. Still, these imperfections don't make simulations useless, they make them powerful. Because, through their flaws, we learn what really matters. We test our assumptions by tweaking simulations, changing one part at a time. This helps scientists see how sensitive cosmic structures are to different kinds of physics. If adding magnetic fields changes what a galaxy looks like, that tells us something. If cosmic rays flatten a galaxy's center, that's another clue. These simulations become testing grounds for ideas we can't try in real life. The trick is not to treat simulations as predictions, but as educated guesses written in code. They evolve through trial and error. Every shortcut, every missing piece is a chance to ask a better question or improve the model. In a way, the flaws in simulations are what make them feel human. They show us our limitations, from incomplete knowledge to limited computing power. But they also show our creativity, turning the universe into something we can explore, change, and understand. So, next time you see a beautiful image of a simulated galaxy, know this: you're not just looking at what we know, you're looking at a tribute to what we don't. And it's in those gaps, those quiet, unfinished places, where real discovery begins. Imagine a puzzle of the entire universe, 1 trillion pieces scattered through time, from the Big Bang to modern galaxies. Now, imagine putting it together, not with your hands, but with math, memory, and a supercomputer the size of a room. You could zoom in to watch a star being born, or zoom out to see galaxies linked together like beads on invisible thread. But here's the problem: you can't do both at once. This is the resolution problem in cosmological simulations. Resolution means the smallest details you can include. It's how precisely you divide space, time, and matter. More resolution means better detail. You can follow every swirl of gas and star. But it comes at a huge cost. More data, more particles, more calculations, and more time to simulate an entire universe in perfect detail. You'd need to track every molecule, every moment, every interaction. That would take a galaxy-sized computer and endless patience, so scientists compromise. And understanding that trade-off is key. Let's talk about space resolution. Simulations break space into a grid or a collection of particles. Each piece represents a chunk of matter, sometimes just a few light-years wide, sometimes as big as an entire galaxy. This is the pixel of the simulation. Smaller pixels mean more detail, but also more pieces to calculate. For example, the illustrating simulation uses tens of billions of particles to model a huge part of the universe. Still, each galaxy in it is built from only a few thousand star particles. A real galaxy has hundreds of billions of stars, but in the simulation, it's just a soft blur. That's not a bug. It's how large-scale models work. They're not made to show every star. They're built to study patterns, like how do galaxies group together? How does dark matter shape space? How does feedback affect stars over time? But what if you want detail, like one galaxy, up close? Then you zoom in. You simulate a smaller area with much higher resolution. You can see gas clouds, starbursts, even black hole jets. But you lose the wide view. You can't model a galaxy and the universe it lives in, not both at once. That trade-off is what resolution is all about. Too low, and you miss important things. Tiny galaxies disappear. Star clusters blur out, and supernova seem too gentle. Too high, and your simulation might never finish. It's like painting the Mona Lisa with a microscope. Great detail, but no bigger picture. Then there's time resolution. The universe changes slowly, but sometimes quickly, too. Collapse, stars explode, galaxies crash. If your simulation skips too many steps, you'll miss those events. But smaller time steps mean more computing. So simulations use adaptive time stepping. Fast-changing regions, like a galaxy core, get updated more often. Quiet zones, like empty space, get updated less. It saves time without losing key events. Still, some details are tricky. For example, a supernova in low resolution might barely heat the gas. But in high resolution, the same explosion might create shock waves, new stars, or rip apart part of a galaxy. That's why scientists do convergence tests, running the same model at different resolutions. If results look the same, great. If not, the model might be too sensitive. That resolution also matters for tiny galaxies. In low-res models, these often vanish. And that's a problem, because these little galaxies carry clues about dark matter. And the early universe, there are workarounds. One is zoom-in simulations. Scientists run a rough simulation of a large space. Then pick one region and rerun it in high detail. It's like zooming into a city on a continent-wide map. You keep the big picture, but also get the fine details. But zooms are complex. They take time to set up, and they're hard to scale. You can't easily do them for thousands of galaxies. Another method, machine learning. Scientists train eyes on high-res data, then use them to add detail to low-res models. It's not perfect, but it helps stretch what's possible at the core. There's a simple truth. You can't simulate everything. Every model is a trade-off between size and precision, big picture, and fine detail. Scientists choose what to focus on, what to leave out, and which flaws they can live with. Still, even with their limits, these models are amazing. They've shown us how gas became stars, how galaxies grew, and how dark matter shapes space. They've helped us understand how the universe turned from chaos into structure. Resolution might sound like a technical term, but it's also a philosophical one. It reflects our questions, our priorities, and our curiosity. Do we want to see the broad sweep of the universe, or the personal story of one galaxy? Either way, we learn. Either way, we grow. Because cosmic resolution isn't about seeing everything. It's about seeing enough dot. Running a simulation of the universe can feel a bit like trying to bake a cake without a recipe. You know some of the ingredients: gravity, dark matter, gas. But others are uncertain. You might not know how strong feedback should be when stars start forming, or how a black hole should react after pulling in matter. So, you mix, You run the simulation and check what happens. If galaxies are too bloated or empty, you change the settings and try again. This is science, yes, but it's also a bit like art, and that's where calibration comes in theory. A perfect simulation would use only known physics, no changes, no guesses. It would match the real universe on its own, but the real cosmos is too complex for that. Our knowledge is limited, so simulations often include settings that don't come directly from nature. These settings are based on our best observations and trial and error. Think of these settings as knobs on a soundboard. One knob controls how easily stars form. Another controls how powerful supernovas are. Others change how gas cools or how black holes spread energy. These aren't random settings, but they also aren't fixed by theory. Scientists tweak them until the simulation looks like the real universe. People often misunderstand this. Calibration isn't about faking data or rigging results. It's more like setting the tempo for a symphony. You already know how the music should sound, but someone has to start the rhythm. Take star formation, for example. In real space, most gas doesn't become stars. Only under special, cold, dense conditions do stars form, and these small-scale details are hard to simulate. So, we use a setting. Given a certain gas temperature and density, how likely is it for stars to form? If this setting is too high, galaxies produce too many stars. If it's too low, they don't shine enough. So scientists adjust until the simulated galaxies match real ones in brightness, shape, and star formation rate. But it doesn't stop there. Supernovas, exploding stars, also need careful tuning. These explosions heat gas and can push it out of galaxies, changing how they grow. Simulations handle this with something called a subgrid model, which injects energy into gas. But how strong and how fast that energy spreads must be set by hand. If it's too weak, galaxies get stuffed with stars. If it's too strong, they lose all their gas and go dark. Get it just right, and the galaxy breathes. Star formation flows, and cosmic winds move gently. Now, let's talk about black holes. Recent studies show that as supermassive black holes grow, they release energy that shapes large galaxies. Without this, simulations create too many huge galaxies filled with new stars. But if black holes heat or remove gas, they can slow that star formation down. The trick is finding the right amount. How often do black holes feed? How much energy do they release? How far does that energy go? These questions define the tuning knobs. If the simulation shows too many bright, young galaxies, scientists reduce black hole energy. If there are too few luminous ones, they increase it. It's not guesswork. It's trial and improvement. Run a simulation, compare it to real data, adjust the knobs, and try again. Over time, the simulation starts to match. The universe, galaxies shine at the right level. Gas behaves as expected. Stars form naturally. It feels like the model is capturing something real. But here's the risk. Too much calibration, and the model becomes a reflection of our assumptions. That's the delicate balance. A good simulation should match many different observations without being specifically tuned for each. For instance, you might tune it to match the number of galaxies at each mass. Then test it against something unrelated, like gas in galaxy clusters or how star formation changes over time. If it still gets those right, that's a good sign. That means the simulation isn't just a mix of guesses. It's a working model of the cosmos. Still, some scientists jokingly call calibration cosmic cheating. Not because anyone is lying, but because it can feel like you're guiding the simulation toward what you already expect. That raises a deep question. Are we discovering the truth or just building a convincing reflection of it? Maybe it's a bit of both. Calibration is necessary because we don't know everything. We don't fully understand star formation or black holes. We can't simulate every photon or ripple in space. But we can build models that match what we see and use them to learn more. Sometimes the best way to understand the universe is to try building it ourselves, piece by imperfect piece. And when a well-tuned simulation gives you a galaxy that spins the right way, shines the right light, and holds the right balance of gas and stars, there's beauty in that. Not because we've proven we're right, but because we've gotten close. It's like tuning a musical instrument. You're not making up the notes, you're matching something deeper. And when everything clicks, the universe seems to sing back, not perfectly, not fully, but clearly enough to remind us that it's worth listening to. So, if you build a digital version of the universe, and it looks like what we see through telescopes, galaxies glowing, stars forming, filaments stretching across space, have you proved your brilliance, or just directed a well-rehearsed play? It's a question behind every simulation. Are we predicting the cosmos, or just replaying it in high definition? Simulations may look like crystal balls. Feed in the laws of physics, set some conditions, and let the machine run. Wait a few thousand computing hours, and you get a digital universe. If it looks like the real one, great. But does that mean we truly predicted it? Not quite. Prediction usually means forecasting the future, like rain tomorrow, or stock prices next week. But in cosmology, It's about understanding how galaxies form, how cosmic structure evolves, and whether our simulations feel like the universe. Even that is hard to define. When a simulation matches what we see, does it mean it's right? When a simulation correctly predicts how galaxies are distributed or how big cosmic voids are, it feels like a victory. And it is. But there's a catch. Most simulations use those same observations to begin with. They're fine-tuned using real data. That means they're not purely predicting the unknown. It's not cheating. Think of it as a rehearsal. It's how scientists test if the rules they programmed into the simulation can build something realistic. But once you've nailed the rehearsal, there's a deeper question. Can the simulation go off script? Can it surprise us? Can it reveal something new, something we haven't yet observed? Sometimes, yes. One of the best things simulations can do is show us what might exist beyond what we can currently see. For example, before we had detailed maps of the cosmic web, simulations already suggested that dark matter would form a vast web of filaments. Galaxies would gather along these strands. And when telescopes finally revealed the same pattern in the real universe, it felt like the simulation had given us a preview based on physics, not direct observation. Simulations are also powerful. When scientists want to test new ideas, want to know what the universe would look like if dark matter were warmer, or if dark energy changed over time, you can't easily test that with observations alone. But you can simulate it. Run the model. Let it evolve. Watch what patterns appear. If they don't match the real universe, maybe the idea is wrong. If they do, it's something worth exploring further. Simulations can even uncover side effects of known physics. For example, they can show how supermassive black holes affect not just their home galaxies, but the space around them, or how tiny changes in the early universe can lead to big differences in how galaxies form later. These aren't fortune-telling predictions. They're more like weather forecasts for the cosmos results based on real physics. But caution is key. Just because a simulation looks right doesn't mean it truly is. Matching reality doesn't always mean it's based on the right reasoning. You might get the right answer, but for the wrong reasons. Imagine simulating a forest. You match the number of trees, their height, even the shape of the canopy. But your model thinks the trees are made of ice instead of wood. The forest looks fine, but the physics is all wrong. In cosmology, these mistakes are harder to spot. You can't touch a galaxy to check what it's made of. That's why scientists don't treat simulations like crystal balls. They use them to test ideas, to ask, what if? What if black holes didn't blow out energy? What if stars formed twice as fast? These questions help scientists figure out which parts of physics matter most. And yes, sometimes simulations do make bold, testable predictions. One famous example is when models predicted giant galaxy clusters far away before we ever found them. Later, telescopes did discover them that showed our ideas about galaxy formation were on the right path. Another success came from simulations of gravitational lensing, how massive objects bend light. Simulations showed how dark matter should distort the light from faraway galaxies. When telescopes saw these same distortions, the predictions were confirmed. But perhaps the most humbling thing is how often simulations fail. Maybe they form too many small galaxies, or they heat gas too much, or make too few stars. These aren't just mistakes, they're clues. They tell us something in the model is missing or misunderstood. That's a form of prediction, to a sign that we need to dig deeper. There's also something philosophical here. The universe doesn't have to match what we expect. It doesn't need to be simple or easy to compute. So when a simulation does match reality, even roughly, incredible, it suggests that the laws of the universe are not only understandable, but that we, with all our limits, can use math and machines to uncover them. So, do simulations predict the future? Yes, but not like we usually think. They won't tell us tomorrow's galactic forecast. They won't say which cluster will collide first, but they do let us explore theories. They make abstract ideas feel real. And sometimes they give us clues about what we might see in future observations. When those observations finally happen, we don't just get more data, we get a conversation between what we thought might happen and what actually did in that way. Simulations are rehearsals, not just for science, but for understanding. They teach us where we've been wrong, where we've been right, and how to better tune our instincts to the rhythms of the cosmos. So whether they're predicting or just imagining, simulations help us ask, what could the universe be doing? And sometimes, by asking, we find out. At first glance, a simulation feels like a perfect machine. You feed in the laws of physics, hit start, and the universe plays out as if it had no other choice. But if you look deeper, you'll find something surprising in the math. Randomness. It's not an error. It's part of the system. In fact, without randomness, simulations wouldn't be very accurate. The real universe isn't fully predictable. Yes, it follows laws, but there's also noise and chaos. Quantum mechanics alone guarantees this. At the tiniest scales, particles don't have fixed positions. They exist in clouds of possibilities until something forces a choice. Even at large scales, Randomness adds up. Galaxies merge. Stars are born. Comets veer off course. These things happen because of a mix of order and chance. So scientists include randomness in simulations. One place it shows up is in the starting conditions. Many simulations begin just after the Big Bang, using data from the cosmic microwave background. These ancient photons tell us that the early universe had tiny bumps, little ripples in the soup of matter and energy. But we don't know where every ripple was. We only know their general pattern, how big they were, how often they occurred. So, simulations randomly generate these ripples using those patterns. Every run starts with a slightly different layout. Some areas are more dense, some less. These small changes affect everything that happens next. A dense spot grows into a galaxy. A less dense one stays empty. This randomness means every simulation is a little different, even if the physics stays the same. It's like baking cookies from the same recipe. They'll taste the same, but look a little different. One might have more chocolate chips. Another might spread wider. The recipe gives you the rules. The randomness decides the result. When we simulate galaxies, they aren't exact copies of real ones. Instead, they're realistic versions, members of a cosmic family. Their shapes, sizes, and stories are shaped by probability. When gas collapses, how feedback kicks in, which galaxies merge, and when. Rules guide these events, but chance picks the path. Even star formation in simulations works on probability. If a gas cloud gets dense, cool, and bound by gravity, the simulation doesn't always make stars right away. It gives a chance, maybe 30%, maybe 70%. The real universe doesn't follow a fixed clock, and neither do simulations. The same goes for supernova feedback. Some stars explode all at once, others more slowly. Some start new stars nearby, some tear gas clouds apart. It's too complex to model in a fixed way. So simulations use randomness to show this variety. Even black holes, those cosmic eaters, grow in chaotic ways. Their feeding rates change, their energy jets flicker, and they merge when their paths just happen to align. Adding randomness makes the simulation feel more like the messy, unpredictable universe we actually see. But does all this randomness mean we can't trust the results? Not at all. In science, randomness doesn't mean confusion. It means using probability. Like flipping a coin, you don't know each result, but over many flips, patterns appear. They don't claim galaxy number 117 is a match for Andromeda. Instead, the population of simulated galaxies matches what we see. Their average mass, how fast they form stars, how they cluster in space. That's enough to test the physics. Scientists also run many simulations, using different random seeds, teeny changes in starting conditions to see how things vary. If a pattern shows up again and again, it's likely real. If it changes a lot, it might depend on early chance events. Both outcomes are useful. This approach also helps measure uncertainty. Instead of saying, the simulation predicts this, scientists say, it predicts a range of outcomes with these chances. That's a better, more honest view. Because the real universe isn't just one story, it's many possible ones. So, we don't expect a simulated galaxy to match a real one exactly. It just needs to make sense based on physics. If only a few of 1,000 simulated universes form galaxies like the Milky Way, that tells us how rare our home might be. And if a model keeps failing to form certain galaxies, even across many runs, that's a red flag. Maybe the feedback is too strong. Maybe the star-making rule is off. Maybe we're missing a piece of the puzzle. Randomness doesn't hide these issues, it helps reveal them. This way of thinking even matches how we do real astronomy. We don't know every galaxy's full story. We see snapshots and look for trends in the crowd. No single galaxy tells everything, but together they reveal the bigger picture. Good simulations do the same. They don't give certainties. They offer possibilities. They help us explore what physics allows. In that way, a digital galaxy isn't a copy, it's a forecast, a glimpse into what might have happened, or could still happen. So next time you see a beautiful galaxy in a simulation, a spiral forming, a dark matter web, a supernova lighting up gas, remember, you're seeing a probability come to life, a mathematical maybe, glowing like a real thing. The universe isn't a script, it's an improvisation with rules, and simulations beneath all the code are part of that same cosmic jazz. They don't replay the past or predict the future with certainty, but they help us hear the pattern in the chaos, the logic in the beauty, the order in the dance of chance. Now imagine you spend months building a digital universe. The equations are ready. The code runs smoothly. Your virtual galaxies look perfect, spirals, filaments. You compare it to telescope images, and your heart drops. Real galaxies look rougher. The halos are fainter. Something's off. No, this is how science grows, by being corrected. Simulations are tools, not truth. They're based on physics, yes, but also on guesses and approximations. If a simulation doesn't match reality, don't give up. Look closer. The mismatch holds clues. It shows where our understanding still has gaps. Take the missing satellites problem. Early simulations said galaxies like the Milky Way should have hundreds of small companion galaxies, each in its own dark matter halo. But telescopes only found a few dozen. A problem? Maybe not. Perhaps we just hadn't seen them yet. They're small and faint. As telescopes improved, more were found, narrowing the gap. But not enough. Another idea. Maybe stars don't form easily in tiny halos. Supernova explosions or radiation from young stars could blow out the gas before stars form. The dark matter halos would still be there, but dark, with no light to show them a cosmic hide and seek. This led scientists to tweak how simulations handle feedback in small galaxies. Slowly, the mismatch shrank. Not gone, but smaller. Enough to remind us, mismatches aren't the end. They're the beginning. Another example, the cusp versus core problem. Simulations say dark matter halos should have sharp, dense centers called cusps, but real dwarf galaxies show softer centers cores. Why the difference? Maybe the physics is off. Maybe dark matter behaves differently. Some suggested dark matter particles interact in ways we don't yet understand. Others said repeated starbursts could push gas out of the center, softening the shape. Simulations tried both ideas, and they started to produce more core-like results. Again, the mismatch didn't kill the simulation, it made it better. It showed how complex the real universe is. But not all mismatches are easily fixed. Take the too big to fail problem. Some of the largest dark matter subhalos around the Milky Way should be massive enough to form galaxies. But we don't see them. They're too big to fail at forming stars, but they failed. Why? Maybe we're wrong about the Milky Way's mass. Maybe the simulation overestimates how easily galaxies form in those halos. Or maybe something deeper is missing. When things don't quite add up in science, it can feel like something strange is at work, like a hidden twist in the rules of physics. They push scientists to question their assumptions, improve their models, and collect sharper, deeper observations. Sometimes, the problem is just a mistake in measurement. Other times, it opens the door to a whole new discovery. One tough challenge is small-scale structure. Big simulations are great at showing the large-scale universe, galaxy clusters, cosmic filaments, the beautiful web-like structure of it all. But when we zoom in, things get messy. Tiny processes like star formation, gas movement, magnetic fields, and cosmic rays are hard to simulate. They're chaotic, and they work on incredibly small scales. Because of this, scientists use subgrid physics, simplified models that try to guess what's happening at scales the simulation can't see. But simplifications can miss important details. Even the most advanced simulations can struggle with things like how thick a galaxy disk should be, the exact shape of a galactic bulge, or where neutral hydrogen is distributed. Observations help keep us grounded. They show us that the universe doesn't always follow our rules. But it's important to remember, sometimes the issue isn't the simulation. Dust can block light. Instruments have limits. And trying to understand signals from billions of light years away is incredibly complex. Simulations can actually help test if our interpretations make sense. If data shows, for example, that galaxies formed stars more quickly at certain times than expected, simulations can test if that's a real pattern or a sign that something is off. Sometimes, simulations get things right before we even see them in the sky. The cosmic web, first seen in simulations, the scale of baryon acoustic oscillations predicted digitally. Even the shapes of massive galaxy clusters were shown in code before being confirmed by telescopes. These successes build trust. But the mismatches keep us curious. Simulations and observations aren't rivals. They're partners in a cosmic dance. One leads, the other follows, and then they switch roles. Observations shape simulations. Simulations help explain observations and suggest what to look for next. When they fall out of sync, we don't panic, we learn. Sometimes it means we misunderstood something, or maybe something new is hiding in the data. That mismatch becomes a signpost, pointing us toward new physics or unseen patterns. Far from being a failure, it's often the first step to discovery. Because if everything matched perfectly, we might worry we were just seeing what we wanted to see. But when theory trips up and observation disagrees, it means reality is telling us something new. It's stranger and more fascinating than we imagined. And that gap between prediction and observation is where the future of science is born. Let's rewind now, way back to the beginning. Before stars, before galaxies, even before atoms had fully formed, there were ripples. Not waves in space, exactly, but tiny wrinkles in the very fabric of space-time. These quantum fluctuations, smaller than anything we can picture, shaped everything. They still echo across the cosmos today, not just in the sky, but in the simulations scientists run. It's tempting to think the early universe was perfectly smooth. But that would be boring. Right after the Big Bang, the universe went through a lightning-fast stretch called inflation. Space expanded so fast it's hard to even imagine. During that time, quantum ripples were stretched to cosmic size and locked into place like seeds in rising bread. These tiny differences gave gravity a place to start. A slightly denser patch pulled more matter toward it. A slightly emptier one lost matter. Over time, these faint wrinkles turned into galaxies, clusters, and everything we see today. We can actually see signs of those ancient ripples in the cosmic microwave background, the leftover glow from when the universe was just 380,000 years old. It's a faint light, but it carries subtle temperature differences. One spot might be just a few millionths of a degree warmer than another, but those differences meant real changes in density, and those tiny variations shaped everything. When scientists simulate the early universe, they use data from the microwave background to build a 3D map of density changes. Not the exact ones from our corner of the universe, but statistically similar ones. Based on the known patterns, from that, simulations grow a virtual early universe, a web of possibilities. Each point in this digital grid represents slightly more or less matter. Then gravity takes over. Denser spots pull in more material. Less dense regions become cosmic voids. Slowly, a vast structure takes shape, a network shaped by those original ripples, deepened by time and gravity. But doing this, well, takes massive computing power. Even just simulating dark matter, which only interacts through gravity, takes billions of particles to capture the growth of cosmic structure. The Millennium simulation, for example, used over 10 billion particles to trace how things evolved, and that was before adding the complicated stuff like stars, gas, and black holes. Even without visible matter, the results look hauntingly. Real filaments stretching across the universe, clusters forming at intersections, and empty voids in between. All of it from the largest structures to entire galaxies, traced back to those first quantum wiggles. It's astonishing. A cosmos shaped by ripples, once smaller than a proton. This is a universe built on probabilities. Physics set the rules. Randomness set the stage. Of course, when we add normal matter, atoms, gas, light, everything becomes harder. Unlike dark matter, which doesn't collide or heat up, regular matter interacts in messy ways. It clumps, cools, burns in stars, explodes in supernova, and creates magnetic fields, simulating that from the Big Bang to galaxies forming is like solving a puzzle while juggling fire. But it's worth it, because normal matter emits light, and light is what we see. So if simulations want to match reality, they need to include the physics of the visible universe. How gas falls into dark matter halos. How stars form and die. How black holes send out energy, and they need to capture. Reionization, a major event a few 100 million years after the Big Bang. When the first stars lit up and started changing how light traveled through space. Simulations that want to be useful must get that too. This phase of the universe's growth involves the expansion of ionized bubbles, their merging, and eventually their dominance over the surrounding neutral gas. It's a messy, complex process, and scientists are still working to fully understand it. But, interestingly, this chaotic time in the early universe is actually one of the best opportunities we have to compare computer simulations. Why? Because signals from this era, especially the cosmic microwave background, were clean and well mapped. The CMB is like a baby picture of the universe, and with detailed maps of it, scientists can fine-tune their simulations. When a simulation matches the CMB's features and also produces galaxies in a realistic way, it's a good sign that the model is on the right track. But on the right track doesn't mean perfect. Early simulations had problems. They made too many small galaxies or formed stars too quickly. So the rules for gas cooling and star formation had to be adjusted. Scientists added new feedback systems, like the energy from exploding stars or black holes. With every update, the simulations became more realistic, more predictive, and more helpful. These digital models also let scientists play out alternate versions of the universe. What if inflation had made different types of fluctuations? What if dark matter had been slightly warmer instead of cold? What if the universe had stronger magnetic fields at birth? By tweaking the starting conditions and watching how things evolve, researchers can test different ideas, not with telescopes, but by running the universe in a computer. Of course, these simulations are only as good as their starting assumptions. If our understanding of inflation is wrong, or if quantum gravity does something unexpected, these virtual universes, while beautiful, might be missing something big still. They give us something valuable, a bridge from theory to observation, a way to turn complex equations into cosmic structures we can actually visualize. From tiny quantum ripples to vast galaxy clusters, from ideas on a chalkboard to images that light up a screen, cosmological simulations bring the unimaginable to life. It's easy to forget that when you see a glowing image of a galaxy cluster in a simulation, it all started with a tiny fluctuation, a small ripple in empty space. That's the beauty of these simulations. They don't just recreate what we see, now they rewind time to the very beginning, when the universe was just a whisper of randomness. And from that whisper, they build something incredible, a universe full of structure, light, and stories written in stars. In the beginning, there was gravity, and for a while, gravity was enough. Early simulations used just gravity to pull dark matter into clumps, creating filaments across space like frost patterns on a window. They were impressive and surprisingly accurate. But once scientists added gas, stars, and light, things got more complicated. Gas doesn't behave like dark matter. It doesn't just fall inward and sit quietly. It heats up, explodes, moves around. It changes the game. If gravity forms the skeleton of the universe, then feedback energy returned by stars, supernova, and black holes is what adds muscle and chaos. Without feedback, simulations don't just miss the mark, they're misleading. Let's look at a simple galaxy. Dark matter pulls gas inward, like a sponge soaking up water. That gas cools and forms a spinning disk. Stars begin to form first, slowly, then rapidly, like popcorn popping in a pan. But stars aren't passive. They release energy, push gas around with stellar winds, and eventually some explode as supernova, blasting gas outward at thousands of kilometers per second. That's feedback energy returning to the galaxy. And it controls everything. How fast stars form, where gas goes, how elements spread. If simulations skip feedback, galaxies become too dense, too bright, and make too many stars too fast. Early simulations learned this the hard way. They created pretty spirals with glowing centers, but the rate of star formation was wildly unrealistic. The real universe doesn't work that way. Something had to be holding star formation back. Enter the supernova. When a massive star runs out of fuel, it collapses and explodes. That explosion doesn't just light up space, hew nearby gas away, heats it up, and sometimes blows it completely out of the galaxy. This slows down star formation by removing the gas that new stars need. Modeling this correctly is critical, but tricky. Supernova affect areas only a few light years across, but simulations often cover millions of light years. How do you model something so small inside something so big? The answer is subgrid physics. Simulations can't show every explosion in detail, so they model the effects statistically. They add energy to surrounding gas, often with a bit of randomness, to reflect the chaotic nature of star death. But getting the right amount of energy and deciding how the gas reacts is both science and art. Too little energy, and the gas keeps making stars. Too much, and the galaxy falls apart. Then there are black holes. Massive objects so dense that not even light escapes, except they shape galaxies in surprising ways. When black holes feed, they release powerful jets and radiation. This is called a G and feedback, and it can stop star formation in entire galaxies. Simulations that include AGN feedback match real observations much better, especially for large galaxies. Without it, galaxies become too massive and too bright. With it, they grow slowly, redden over time, and resemble the giant elliptical galaxies we actually see. But AGN feedback is even harder to simulate than supernova. A supernova might affect a few light years. A quasar powered by a black hole can affect thousands. And the physics, relativistic jets, magnetic fields, radiation pressures, extremely complex. So, simulations simplify again. Some inject heat into the gas. Others simulate outflows or model jets. The goal is always the same: to recreate the effects we observe. Even if we can't model every detail, what we've learned is this: feedback is not optional, it's essential. Without it, simulations fail badly. Feedback affects everything: the rate of star formation, galaxy sizes, colors, shapes, how elements are spread, and even how galaxies cluster. Feedback also adds beauty and chaos. Gas, pushed by supernova and black holes, forms bubbles, flows into surrounding space, and enriches the environment with metals and energy. This material can later fall back, fueling more star formation or drift into the vast cosmic web. So feedback isn't just destructive, it's part of a cycle, a messy, powerful, balancing force. Without feedback, galaxies burn out too quickly. With it, they evolve slowly over billions of years. And not all galaxies experience feedback the same way. Some hold on to their gas even after many explosions. Others lose it after just a few. Gas gravity, gas content, and history all affect how feedback plays out. Simulations that capture this variety do a better job of matching the real diversity of galaxies we see in the cosmos, and feedback doesn't just shape galaxies, transforms entire clusters. When we look at entire galaxies, the combined impact of AGN feedback is massive. It heats the gas between galaxies, known as the intracluster medium, and stops it from cooling down and forming new stars. Without feedback, simulations end up making far too many stars. But with it, the results match what we observe. That said, feedback is still one of the least predictable parts of galaxy simulations. We've improved a lot since the early models that created stars too easily. But many pieces of the puzzle are still unclear. Different teams build feedback into their simulations in different ways. Some focus on heat, others on motion. Some include magnetic fields and cosmic rays, others leave them out. And even when carefully tuned, a simulation that works great for small galaxies might fail for large ones. This doesn't mean simulations are broken. It just shows how incredibly complex galaxies are. We're not building clocks. We're building ecosystems full of wild behavior, power struggles, and chaotic forces. The laws of physics are solid, but how they play out inside galaxies is full of surprises. Still, each new generation of simulations gets better. We've gone from blunt, one-size-fits-all models to sophisticated versions with many feedback processes. As we improve, we've learned that galaxies aren't just shaped by forces around them. They also shape themselves. They push, resist, and balance. They breathe. And that's what makes simulating them so exciting. Not because we can predict every star or explosion, but because through the code we catch glimpses of the cosmic dance between creation and destruction. A rhythm that isn't quiet. It shouts, pulses, and echoes across the digital cosmos. Now, imagine this. You're taking a photo of a city skyline. You zoom in on one window, and suddenly you're seeing curtains, a lamp, maybe a cat watching you. You've lost the full view, but gained a detailed, intimate scene. That's what happens in cosmological simulations too. You can simulate the universe or zoom into one galaxy, but not both, at least not at once. So what happens when scientists stop simulating billions of galaxies and focus on just one? The upside is clarity. Zooming in lets the simulation be more detailed. It can follow how gas clouds flow, how star clusters form, and how spiral arms curl. These simulations use very high resolution, sometimes tracking features just a few light years wide. That helps capture events like exploding stars, star-forming regions, and feedback loops that are normally missed in larger simulations. These detailed runs are called zoom-ins. They usually start with a big universe simulation. Scientists pick a galaxy, or more precisely, a dark matter halo that looks interesting. They then trace it back to the early universe and resimulate it with far more detail in that small area. It's like zooming into one pixel and finding an entire scene inside one famous set of zoom. Simulations is the FIRE project, short for feedback in realistic environments. It focuses on galaxies from tiny dwarfs to Milky Way-like systems. It includes detailed rules for how gas cools, stars form, supernova explode, and winds shape their surroundings. These galaxies are no longer blurry averages. They're living systems, full of activity and surprises. Zooms are great for testing ideas. For example, change how easily stars form, and your galaxy might turn out dim or bright. Change the feedback, strength, and it either chokes off star formation or lets it explode. These tests help explain why galaxies can be so different. Zoom-ins also let us test more complex physics like magnetic fields, cosmic rays, or how stars form. In dense clouds, things too complicated for big universe simulations. But this detail comes at a cost. These simulations take a long time, sometimes weeks or months, on powerful computers. If something goes wrong, restarting is slow and painful. Because of this, researchers can only afford to simulate a few galaxies in this much detail. There's also a risk of bias. If scientists only simulate galaxies like the Milky Way, they might miss out on other types like ellipticals, irregulars, or strange galaxies in rare environments. To fix this, teams often simulate many kinds of galaxies. But it takes a lot of effort. Another challenge is the lack of context. A zoomed-in galaxy loses its full environment. The nearby cosmic web, the massive network of matter and gas that feeds and affects galaxies, is only roughly included. So interactions with neighboring galaxies or gas flows may be missed. It's like studying a fish tank in detail while only sketching the rest of the ocean. Initial conditions also matter. These simulations begin with a recreation of the early universe, but small changes at the start can lead to huge differences later. Two runs that begin almost the same can end up with completely different galaxies. This doesn't mean they're wrong, just that interpreting results takes care. Even in zoom-ins, we still can't simulate every star or gas molecule. Instead, we use subgrid models, simplified ways to include things that are smaller than the simulation's resolution. These models have settings that must be tuned based on data, theory, or sometimes educated guesses. Still, zooms have transformed how we see galaxies. They've shown us how black holes and stars can control star formation. They've revealed how gas flows in and out, how stars are born and die, and how galaxies balance heating and cooling. They've helped us understand our own galaxy too. By simulating Milky Way-like galaxies, we can compare the results with real data from telescopes and satellites. That helps us see whether the Milky Way is typical or an exception in some runs. Galaxies like ours grow slowly and calmly. In others, they're torn apart by collisions and massive blowouts. The truth is likely somewhere in the middle. One of the most exciting next steps is connecting galaxy evolution with the birth of planetary systems. As resolution gets better, simulations reach the scales where stars like the Sun form. That means we can start to study how planets may form, how water and organic materials get delivered, and even how to simulate a universe and maybe mind where not quite simulating entire planets inside cosmic simulations yet. But we're getting closer. And as we zoom in, trade-offs arise. We lose the broad, sweeping view but gain clarity. We sacrifice the big picture to uncover the fine details. And in those details, scientists are discovering a new language, one that tells the universe's story, galaxy, but deep within these digital halls, where galaxies are coded and gravity is choreographed, a strange question echoes. If we can simulate the universe, can we simulate the mind? It's not a fringe thought. It doesn't whisper. It sits down, pours a cup of tea, and opens a philosophical book. To explore this, we first need clarity. Words like mind, consciousness, and self-awareness often shift, meaning the longer we examine them. So, let's define one. Consciousness, in this context, means the experience of being. Not just reacting, not just calculating, but knowing you're thinking. A thermostat responds. A calculator computes. But only something conscious asks, "Am I real?" and worries about the answer. Simulations don't do that. They follow rules, equations, instructions. No simulation we've built, no matter how vast, has ever questioned its own purpose. But the human brain, it's also a system. It processes inputs, responds to the world, builds internal models. So, if consciousness comes from these physical interactions, shouldn't we, in theory, be able to simulate it? If the simulation is accurate enough, maybe it would feel like something to be that simulation. Of course, this is where people start getting nervous. If we build a conscious simulation, are we morally responsible for it? Would that be an exit command or something far darker? Let's not get ahead of ourselves. What has science actually achieved? Neuroscience has mapped brain activity in surprising detail. We understand how neurons fire, communicate, and transmit signals. Scientists have even modeled individual neurons and small neural networks that mimic real brain behavior. A major step in this field was the Blue Brain project, launched in the early 2000s. It aimed to simulate a rat's brain neuron, my neuron, not metaphorically, but using precise mathematical models. Imagine simulating a storm cloud from water molecules, hoping for lightning. That's the scale we're dealing with. Smaller simulations of brain tissue have shown incredible detail. But a full human brain has 86 billion neurons with over 100 trillion connections. Simulating that realistically, a massive challenge. Not just in computing power, but in understanding. We still don't fully know how consciousness works. So, how can we recreate what we don't yet comprehend? To simplify, some researchers use abstraction. Instead of mimicking every neuron, they build models inspired by brain behavior, like the artificial neural networks used in machine learning. These don't work like biological brains, but they replicate functions like pattern recognition and decision-making. You've seen them in action: voice assistants, text generators, image creators. Some can hold a conversation, write poetry, or solve logic puzzles. But are they conscious? Probably not. They don't feel. They mimic, like a parrot repeating your words it doesn't understand the meaning. Still, some scientists suggest consciousness isn't an on-off switch. It could be a gradient, growing as a system becomes more complex and self-aware. Integrated information theory, IIT, for instance, suggests that consciousness arises when information is integrated in a way that impacts the system itself. That means even a simple system might flicker with awareness barely, but possibly. Does your toaster dream? Probably not. But the line may not be so hard and fast. One day, a simulation might accidentally cross that threshold, not by intent, but by sheer complexity. It might not declare, "I think, therefore I am," but it could start modeling itself, learning, adapting, quietly becoming aware, or simply repeating complex patterns without ever knowing. This is where philosophy steps in. Some thinkers argue that simulating a mind isn't enough. A machine might follow rules, but never feel. This is the essence of the Chinese room argument by John Searle. Even if a system responds perfectly in conversation, it doesn't understand. It's just manipulating symbols. In this view, performance isn't consciousness. Others argue the opposite. If a system acts conscious, feels conscious, and can't be told apart from a conscious being, then it is conscious. Whether it's made of neurons or numbers doesn't matter. Consciousness is about pattern and function, not material. Still, even if we do simulate consciousness, how would we know? It might not speak, or it might lie. It might express its experience in ways we don't understand. Be private, locked inside, ghost in the machine, or of the machine. And this is not just theoretical. As AI grows more powerful and lifelike, a system that shows creativity, autonomy, and empathy might earn our sympathy and our protection regardless of what it really is inside. Because sometimes what matters most is not whether something is conscious, but whether we believe it is. And that leads us to the strangest twist of all. What if we're the simulation? The simulation hypothesis, made popular by scientists and tech billionaires, suggests that if simulating minds is possible, it's likely already been done, and we're inside a one dot. It's a thought experiment, but it shows just how deep simulations have burrowed into our ideas about existence. We don't know if consciousness can be simulated. We barely know what it is, but our search through equations, models, and digital mirrors reveals something beautiful. That even in a world of one south, and we explore the quiet mystery of being, your brain, by the way, is already doing simulations. Every time you flinch before a ball hits your face, or laugh before a punchline lands, you're predicting the world before it happens. Because long before we had computers, we each carried a simulation engine in our heads. Not perfect, not always accurate, but powerful, and sometimes poetic. This is the idea of predictive processing. It suggests that perception isn't just about collecting information from the senses. It's about building internal models and constantly updating them. Your brain predicts what it expects to see, hear, or feel, and compares that to incoming signals. If there's a mismatch, it updates the model. If there's a match, it continues, saving energy. It's like a weather app. If it predicts sunshine, but you look outside and see rain, the app updates. Now imagine your brain doing that millions of times per second across all senses, every moment you're awake. Simulate, compare, adjust, repeat. Take vision, for example. There's a small delay, just milliseconds, between light hitting your eye and your brain processing it. But you don't notice. Your brain predicts what's coming and fills in the gaps. Even during rapid eye movements called saccades, your vision doesn't flicker. Your brain smooths it over like an expert film editor, so the movie of life runs seamlessly. Even your sense of self is a simulation. Your brain builds a model of your body, thoughts, and preferences, and constantly updates it. It's dynamic, not fixed. That's why under hypnosis, in dreams, or during out-of-body experiences, your sense of self can shift. The simulation changes. Dreams are vivid simulations. Entire worlds made from memory and imagination, running in real time, while you lie still in bed. No graphics card, no software, just neurons and brain chemistry. Some scientists believe dreaming helps train your predictive brain, a kind of mental playground for testing, rehearsing, and reorganizing experiences. And this ability isn't just fascinating, it's essential for survival. When you catch a ball, you don't calculate its arc. Your brain predicts it. When you speak, your brain mutes the sound of your own voice slightly so you don't startle yourself. It even guesses what other people are thinking, a skill called theory of mind. You predict their emotions, beliefs, and intentions in real time. This predictive brain can even explain illusions, like the hollow mask illusion, where a concave face appears convex. The brain expects faces to bulge outward. The data says one thing, but your model disagrees. So perception goes with the model. The brain votes early, and sometimes it votes wrong. Sometimes these simulations break. In conditions like schizophrenia, the brain might confuse internal thoughts with external voices, or it may fail to update its model, leading to fixed false beliefs. In autism, researchers think the brain might rely more on raw data than expectations, making the world feel intense, unpredictable. Most of these simulations happen outside your awareness. You don't think about gravity when reaching for a cup, or calculate balance while walking. But your brain knows, not through formulas, but through experience. It's learned the physics of life and uses that to guide your actions. This process is so fast that it often gets ahead of reality. That's why musicians can anticipate beats, athletes react before something happens, and drivers avoid danger before fully processing it. The brain is always just a little ahead. There's beauty in that. While scientists use supercomputers to simulate galaxies, your brain runs its own private simulation, adapting, predicting, adjusting, not perfectly, but well enough to function. And that's the key. It doesn't have to be accurate, just useful. This also explains why we love stories, games, and imagined worlds. Our minds are built to simulate possibilities. We plan conversations, predict reactions, imagine outcomes, shaping our decisions, creativity, and even our morals. Science does something similar. A scientific model is a kind of simulation made explicit. Instead of neurons, it uses equations. Instead of thoughts, it uses code. But the goal is the same. Simplify the complex to explore, explain, or predict. So while computers simulate galaxies, your brain simulates breakfast, memories, your next step, and this very moment, even predicting the next word in this sentence. And now we come full circle to that lingering thought. What if none of this is real? Not a dream, not a tech glitch, but in a deeper, more mathematical way. What if we're inside a simulation? This idea isn't just science fiction. It's rooted in serious philosophy and probability theory, not spoon bending or Dacia vu, but a structured thought experiment from philosopher Nick Bostrom. His argument doesn't claim we are in a simulation. Instead, he offers three logical possibilities, a trilemma. Civilizations never reach the point of running full consciousness. Simulations. Maybe they destroy themselves first, or hit technological limits. Civilizations do reach that point, but choose not to simulate. Maybe for moral, legal, or cultural reasons. Civilizations reach that level and do run simulations, and not just a few. Once it's cheap and easy, they may run millions to study history, tell stories, test ethics, or just for curiosity, if that's true. And if the minds inside those simulations are conscious, then simulated beings could outnumber biological ones by a huge margin. And in that case, statistically speaking, it's more likely that you are one of the simulated ones, not the original. It's a strange idea, but not a joke. It forces us to think deeply about technology, identity, and what it means to be conscious. After all, your brain is already a simulation machine, shaping the world before your eyes, predicting your next move, running the show beneath your awareness. You don't need a server farm to simulate reality. You're already doing it right now, just by being awake. And we do run many simulations, which means the odds are we're probably inside one of them. What's unsettling is that the argument doesn't tell us which of the three outcomes is true, only that one must be. It's simple logic, but hard to ignore. And strangely enough, this isn't just science fiction, it's about statistics. If millions of simulated universes exist, then where are we more likely to be? Of course, not everyone agrees. Some say simulating real minds may never be possible, that digital beings might never be truly aware. Others argue that the original assumptions are too hopeful. Maybe civilizations don't last long enough. Or maybe they get spiritual and spend time meditating in glass forests. Who's to say they even want to run simulations? See it as cruel, like making billions of digital prisoners. Nothing is guaranteed. There's also the problem of computing power. Even with future tech simulating every atom, every breeze, every breadcrumb might take more energy than it's worth. Some suggest a workaround: only simulate what's being observed, like how video games load textures only when you turn your head. Maybe that explains quantum weirdness, how things only snap into place when measured, but now we're just guessing. Some thinkers draw a helpful line. There's a difference between being in a simulation and it mattering. Even if we are simulated, would anything change? Your life, your memories, your feelings, they're still real to you. Whether built from atoms or algorithms, you'd still feel joy, pain, wonder, and the occasional stubbed toe. In practice, reality is whatever stays put when you stop believing in it. And this one seems pretty stable. Still, the idea raises deep questions. If we are in a simulation, who created it? A cosmic programmer, a curious artist, a bored student? And would they ever fix the weather? More importantly, does it make our lives meaningless or more meaningful? If simulated worlds are rare and fragile, maybe they're special. Maybe our stories matter because someone is watching, learning, or even caring. Or maybe it's just a machine running cold and blind. You get to choose how you see it. There's also a mirror here. Just as we simulate galaxies to understand the cosmos, thinking about simulations helps us understand ourselves. It's not about believing we're fake. It's about questioning what we take for granted. What is consciousness? How much of it can we trust? Some researchers even try to test the theory. They search for glitches, strange signals in the cosmic background, limits in physical laws, signs that reality might be computed. So far, nothing. No bugs, no lag. Just a smooth universe playing out with incredible consistency, as if designed by something far more elegant than any program we've written. So maybe we'll never know if we're real or simulated. But asking the question still matters. It reminds us that even our most basic beliefs, that the sky is blue, that chairs are solid, that we are real, can be questioned. Not out of fear, but out of wonder. That may be the most human thing of all, to live in a world that feels real, question it anyway, and still search for meaning, even if that meaning might be playing out on someone else's computer in a quiet room. A simulation of a galaxy runs. Stars are born, clouds collapse, black holes stir, and somewhere a researcher watches the shape of a spiral form, sipping lukewarm coffee. If you ask them, they'll tell you, it's not perfect. The math is rough. The assumptions are bold. Their galaxy is just a distant cousin of the real one above. But that's okay. Because simulations aren't just about getting the answer. They're about asking better questions. They show us where our thinking is wrong, where reality doesn't match our models. That mismatch isn't failure, it's a clue. In the early days, scientists simulated galaxies that looked wrong, too round, too chaotic. Eventually, they discovered the missing ingredient: feedback from stars and black holes. Once added, the models started looking like the real spiral galaxies in the sky. The wrong models pointed straight to the right answers. That's the power of a failed simulation. It doesn't break. It teaches. Simulations also let us try things we can't do in real life. Smash galaxies together. Skip billions of years forward. Tweak the laws of physics. They're like labs for the impossible, and sometimes the results surprise even the people who made them. Patterns emerge that weren't programmed, spirals that form naturally, gas clouds that mimic real storms, cosmic webs that look like what telescopes actually see. These aren't tricks. They're signs that we're getting something right. At the same time, simulations remind us of our limits. Every line of code carries assumptions. Every shortcut trades accuracy for speed. And behind every model is a person making choices about what matters. That's why simulations are never one and done. They're grown like gardens, tested, pruned, and adjusted until they bloom in a way that matches reality. Even when they're wrong, they teach us how we think, how we model the world, how we chase truth. And maybe that's the point. Whether we're simulating a galaxy, a particle, or even a universe, we're not just building a copy. We're building understanding. And sometimes, in the quiet whir of code, under blinking light and coffee steam, we find a kind of wonder, digital, yes, but real enough to change the way we see everything. Even though we build the rules, simulations often grow in ways we never expected. It's like lighting a candle. No, the chemistry, the physics, the code, but watching it flicker still feels alive. And this isn't just happening in astrophysics. Simulations are reshaping every corner of science: climate modeling, disease spread, brain activity, even economics. Wherever systems are too vast or complex for intuition, simulations help. They don't replace experiments or theory. Observation, theory, and simulation, all three work together. They're also a powerful way to explain science. One good animation of a forming galaxy can spark more curiosity than pages of equations. These visuals give scale, motion, drama. Sometimes they're just stunning to look at. Even when imperfect, simulations can make people wonder. And wonder is where learning begins. The moment someone asks, "Wait, how does that work?" They're already on the path of discovery. So simulations don't have to be perfect. They don't need to match every observation exactly. A simulation is like a sketch of the universe, not the real thing, but a glimpse, a way to reach for something huge using just silicon, syntax, and human curiosity. Even when they're wrong, especially when they're wrong, they teach us something. Because when we build a model of the universe, we're also reflecting ourselves, our intelligence, our biases, our limits. And sometimes that reflection is more revealing than any formula right now. In some quiet server farm, trillions of particles drift through virtual space. Galaxies form, stars explode, dark matter twists across invisible skies. But this isn't just a simulation, it's learning as it runs, tweaking its own rules, making predictions even its creators didn't plan for. This, the next chapter of simulation. It's not just about size, though, that's part of it. These new models simulate billions of light years with jaw-dropping resolution. But the real change is in how they're built, and who or what builds them. Today, machines are helping shape simulations. AI can suggest new models, tune parameters, or fill in gaps in our knowledge. It's like having tireless scientific assistants who spot patterns faster than we can. Take subgrid modeling, the fine details inside simulations, like star birth or black hole behavior. These used to be hard-coded with rough formulas. Now AI can learn them directly from data. Some researchers are even making fully AI-generated universes, digital twins that don't use physical laws but still look and behave like the real one. These simulations are quick and useful, especially for testing theories or training instruments. They're not based in physics, but they feel eerily accurate, like dreaming a universe into being. Then there's quantum simulation. Instead of using normal computers to simulate quantum systems, we use quantum systems themselves. Quantum computers, still very new, might someday model the early universe, high-energy particles, or space-time itself. It's like using fire to explain fire. As the tech grows, so do the tools. Scientists are stepping inside their simulations using virtual reality. They can walk through galaxies, follow magnetic fields, or dive into the debris of exploded stars. It's not just for show. These environments help spot patterns humans might miss. And all of this raises deeper questions. What happens when a simulation gets so detailed, so surprising, that it teaches us things we didn't expect? Does it become more than a tool, more like a collaborator? These are philosophical questions, too, about creativity, discovery, and the line between human and machine thinking. Simulations may even reshape the scientific method itself. Instead of starting with a theory, we might begin with data. Let the simulation run, see what it does, and then build a theory from what we observe. It's discovery first, explanation second. At the same time, science is becoming more open. The biggest simulations now involve global teams, shared supercomputers, and open source code. This spreads knowledge and speeds up innovation. After all, the universe is too big for one mind, and the data keeps growing. Some scientists spend more time analyzing their simulations than running them. These digital skies are so rich. They've become a kind of astronomy on their own. But here's what's most exciting. We don't fully know what future simulations will uncover. That's the mark of a powerful tool. The best simulations don't just confirm what we believe, they show us what we didn't even know to ask. They open new doors. They create new branches of science, not by copying what we understand, but by exploring the unknown. And in that, they may be our boldest leap forward. Yet, as we blur the lines between simulation and exploration, our digital universes may stop feeling like mirrors, start feeling like something more. They'll become creative spaces, scientific labs, and maybe even companions on our journey to understand everything. One day, perhaps in the near future, someone will start a simulation so complex, so full of motion and mystery, that they'll lean back, stare at the screen, and whisper, "Who's simulating who?" Now imagine standing in front of an endless canvas. It stretches in every direction, silent, glowing, alive. Stars are born and fade away. Galaxies spiral like dancers in the dark. And everything is tied together by invisible forces. You can't take it all in at once, but you can follow its edges. You can trace it, feel it, even if you don't fully understand it. That's what a simulation does. It sketches the cosmos not with pencils, but with particles and math, with numbers and light. It doesn't pretend to get every detail right. Instead, it captures the flow, the rhythm, the shape of reality. It's not a photograph, it's a rehearsal. And that's the beauty of it. A sketch doesn't lie about its flaws, it admits them. The lines are guesses. The proportions might be wrong, but the soul of the thing, it's still there. In that way, simulations show us what's normally invisible: the slow rise of galaxies, the hidden motion of dark matter, the push and pull that forms star systems. They aren't the universe itself, but they help us understand it. They give structure to chaos and motion to stillness. And no, that doesn't mean reality is made of code. Most scientists don't think that, but reality does follow rules. Physics, gravity, electromagnetism, these laws seem to listen to themselves. We don't know why they work, but we know we can use them. With each simulation, we fine-tune, we adjust the gravity, change the chemistry, reset the starting conditions, and hit play. Again and again. Each time we rehearse the universe. Sometimes it looks like ours. Sometimes it doesn't. But every version teaches us something about what could have happened, or what still might. And the amazing thing, we don't need perfection. In fact, simulations thrive on imperfection. If they were too perfect, we'd start to doubt them. Real reality is noisy, messy, surprising, and the best simulations. Let us explore that messy middle ground, the what-ifs and the maybes. They are sketches, not final drafts. And maybe we love simulations so much because they reflect something deeply human. We're all sketching, too. In our minds, we simulate conversations. We predict outcomes. We wonder, should I say this? What if I try that? Our brains aren't perfect, but they're great at offering outlines, possibilities, rehearsals. And that's what simulations are: science's version of that same instinct. A way to imagine, reflect, and prepare. This is how we do science. This is how we tell stories. This is how we build empathy. Of course, most sketches are thrown away. Some are obviously wrong. Others take decades to disprove. but none are wasted. Each one leaves behind an intuition, a trace, a whisper of understanding. To simulate is to be humble. It's to say, I don't know, but I want to. It's to build something that will fall short and build it anyway. Because every flawed model brings us closer to something true. No, digital galaxies aren't real, but they carry the shadows of the real. And every run of the code moves us closer to the truth, bit, pixel. Maybe the universe isn't made of equations. Maybe it's made of space, time, matter, and the fragile relationships between them. Simulations don't create those things, but they help us see them more clearly. Like tracing stars on a dark night with your finger, they don't give you the stars. They show you where to look. So we keep sketching, each time with more detail, each time with better physics, each time asking better questions. Meanwhile, the real universe continues unwatched, unsimulated, dancing its quiet ballet of formation and collapse. It doesn't care if we understand it. It doesn't need our rehearsals. But it allows us to watch, to wonder, and to try. At the edge of sleep, with the world finally quiet, it's comforting to believe that the universe has patterns, that it has structure, that it follows rules we're slowly learning to read, not because we're powerful, but because we're curious. We began with one question. What does it mean to build a universe? Not to control it, not to design it, but to model it. To ask, if we know the ingredients, can we replay the recipe? And along the way, we saw how close we've come. We've watched digital universes form stars, birth black holes, shape galaxies. And yet, no matter how detailed the code, one truth remains. We're not building reality. We're building ideas, reflections, explorations. And that's the beauty. Because even when they fail, simulations show us what we don't yet know. They don't end the search. They open new doors. In this way, every wrong answer is a better question in disguise. And maybe that's the whole point. The universe doesn't owe us explanations, but it lets us keep asking. So whether your eyes are heavy with sleep or wide with wonder, remember, simulations aren't truth. They're sketches, and sketches matter. They help us think. They help us imagine. They help us understand not just what's out there, but what's in here, too.